I will talk about quantification of low cycle fatigue damage accumulation in stress concentration area by local strain evolution. This presentation was prepared in collaboration with my colleagues, Dr. Pisarev and Dr. Eleonsky. So, outline of presentation. First of all, I will give brief introduction in the problem, and after that I will consider experimental procedure and initial experimental information to construct damage accumulation function, and finally conclusions. So, introduction. Earlier, destructive method employing preliminary low cycle fatigue loading of specimens with holes and inserting a sequence and arrow nodes under constant external load has been proposed to quantify damage accumulation. In this case, we have used both singular, I mean stress intensity factor, and non-singular T-stress fracture mechanics parameters of created nodes as current damage indicators. Numerical integration of normalized evolution curves over lifetime provides damage accumulation function in explicit form. So, using principle inherent in destructive technology to create non-destructive methods to analyze damage accumulation looks like a natural continuation of development methodology. So, scientific novelty of proposed approach decides in introducing damage indicator, which can be determined by optical interferometric measurement performed by using single specimen for given cycle parameters. Evolution of these parameters as a function of number of cycles leads to explicit form of damage accumulation function. So, experimental procedure. The specimen, loading scheme, and the measurement parameters are presented in this slide. Plain specimen made from aluminum alloy 2024 type was used in present research. The specimen has a central hole, diameter 12 millimeters. Drawing of specimen, coordinate system, and measurement displacement components are shown in this figure. Absence of technological residual stresses in the specimen follows from data of the probe hole drilling and further optical interferometric measurement of deformation response to local material removing. Point A, you can see point A, is the critical as most interesting point. Quantitative characteristics of local deformation process have been obtained for different number of loading cycles. Each loading step at which specific reflection holographic interferogram is recorded is defined by removed stress increment. Typical interference fringe patterns obtained in the initial stage of low cycle fatigue are given in these figures. Initial experimental information. Distribution of displacement components and relative strain along the whole edge for case of third loading cycle are presented in these figures. Its initial experimental information for damage accumulation analysis. Here you can see interference fringe patterns obtained at different stages of low cycle fatigue. The obtained experimental data provides the dependencies of local strain at point of maximum strain concentration, its critical point A, as a function on the remote stress level for all considered cycles. It can be seen that linear functions related to the 218 and so on cycles are practically coincident and depicted by the single straight line. These pictures. Dependencies of deformation parameters, namely circumferential and normal strains to the specimen surface, as a function of number of cycles, which are essential for further deriving current damage indicators, are shown at these figures. Damage accumulation analysis. Now we have introduced into consideration the damage accumulation function dm, which characterizes current damage degree proceeding from the evolution of deformation parameter referred to whole edge. Variation of this function during low cycle fatigue is described by equation 1. The damage accumulation function can be derived by integration of equation 1. In this case, explicit form of damage accumulation rate, psi, can be presented by equation 3. Substitution of damage accumulation rate, psi, into relation 1 and summarizing along the segment delta nm at end of point of which values chosen okay, have been determined instead of integration gives explicit form of the damage accumulation function. Evolution of normalized current damage indicator as a function of number of cycles are presented for critical point R in these figures. As a result, the damage accumulation function dm is constructed from evolution different damage indicator. This result clearly evidences practically the same damage accumulation functions, which follow from 3 different damage indicators. This fact firstly demonstrates highly accurate character of the measurement procedure based on reflection, hologram interferometry. Second, revealed coincidence confirm a high representative level of all 3 damage indicators which are involved in the consideration. This fact is also important from the experimental standpoint. And conclusions. Novel non-destructive method of quantitative description of low cycle fatigue damage accumulation near open hole is proposed and implemented. The main scientific novelty of the development approach resides in involving evolution of directly measured deformation characteristics due to low cycle fatigue as current damage indicators. These parameters include maximum circumferential strain range, maximal circumferential strain values, and maximum normal strain range. All these values refer to the critical point belonging to the edge of hole, since they are obtained without local removal of material in the form of narrow notch. The last fact is of decisive importance and means the damage accumulation function can be constructed by single specimen using forgiven stress range and stress ratio. Previously developed destructive methods needs around 8-10 specimens of same dimensions to reach above mentioned goal. A capability of considering an instant of short crack appearance on the specimen surface as a second limit case in the course of obtaining the explicit form of damage accumulation function is the second remarkable peculiarity of proposed approach. Thank you very much for your attention.